the television, the iron, and the air conditioner. All these need electricity to function. Just about everything in this day and age runs on electricity. What then is electricity? Electricity is a flow of electrical charges. Before charges can flow, there should be a conductor. Conductors are materials that allow electrons to flow freely through them. But even more important, there should be a source and driver of these electrons. This will usually be a cell or battery. When the battery is connected across the ends of the conductor, chemical reactions inside the cell push electrons from the negative terminal to the positive terminal. In a circuit, we'll learn more about this shortly. Current is usually shown as flowing in a direction opposite the flow of electrons. Current is therefore shown as moving from the positive terminal of a cell or battery to a negative terminal. Electrons are negatively charged, so they are repelled by the negative terminal and are drawn towards the positive terminal. Conventional current, on the other hand, thought to be the flow of positive charges, are repelled from the positive terminal and drawn towards the negative terminal. Once electrons flow, current flows in the opposite direction. The path through which the current flows from the positive terminal to the negative terminal is referred to as a circuit. We'll learn more about this later. Electric current is measured in a unit called amps or ampere. 1 amp is 6 times 10 to the power 18 electrons per second. Currents can be measured using an ammeter. Smaller currents can be measured using a milliammeter. An ammeter is usually connected in series to measure the current in a circuit. The unit of charge is the coulomb and can be defined in terms of ampere. 1 coulomb is a charge passing any point in the circuit when a steady current of 1 ampere flows for 1 second. Mathematically then, charge is equal to current times time. Charge is measured in coulomb, current is measured in ampere, and time in second. Therefore, 1 coulomb is equal to 1 ampere second. Let's talk more about circuits now as we consider circuit diagrams. There should be a complete path, normally referred to as a circuit, for current to flow. The conducting path usually consists of copper wires, which is a conductor, battery, switch, lamps, among other things. Various parts of the circuit are represented using circuit symbols. Some of these circuit symbols are: 1. The cell. This converts stored chemical energy into electrical energy, allowing positive charges to flow from the positive to the negative terminal through an external circuit. A combination of cells gives a battery. Later on, we'll find out that this kind of combination is series. A switch controls the flow of electrical current in a circuit. It initiates the flow of current when it is turned on or when it is closed, and stops the flow of current when it is off or when the switch is opened. A resistor opposes or limits the flow of electric current. The strength of this opposition is termed as resistance. A resistor has 2 symbols as indicated there. Either the rectangular one or the zigzag one can be used in a circuit. A variable resistor is a type of resistor whose electrical resistance can be adjusted. So unlike a normal resistor, a standard one whose resistance is fixed when it is used in a circuit, a variable resistor can have its resistance change over a range. And it also has 2 symbols with an arrow drawn across the symbol of a resistor. The next one is a bulb. The bulb also has two symbols that can be used in a circuit. A bulb converts electrical energy to light. A bulb is referred to as an electrical load because it consumes the energy or power flowing through the circuit. The component of the circuit that is used in measuring current is the ammeter. It is usually connected in series with a device to measure the current flowing through it. The voltmeter is used to measure voltage or potential difference in a circuit. It is usually connected in parallel with a device to measure its voltage. So we have all these components. How do we connect them? We need a connecting wire. This could be a copper wire typically. And in a circuit, we represent a connecting wire by means of a straight line. If you see connecting wires drawn such that there is more like a dot between them, it represents a junction. So these two wires are joined. If you see them crossing each other like it's indicated in the third one, then it means they are crossing but they are not joining. So then how do we make our connections? The circuit components could be connected in series or in parallel. For series connection, the different components follow one after the other, and there is just one path for current to flow. Cells are connected in series when we have the negative terminal of one cell connected to the positive terminal of the other, and this is normally how a battery looks like. And more often than not, you could be tested on the total voltage. We'll learn more about voltage in the next video. For cells in series, the total voltage is the sum of the individual voltages of the cells put together. So for n number of cells, our total voltage Vt is equal to V1 plus V2 all the way to Vn. That is not too difficult to remember, is it? Then we have resistors in series. Again, one resistor follows the other, and we have the same current flowing through the circuit when they are connected in series. The total voltage in the circuit is shared amongst the resistors, and we'll learn more about this as we move on. How then do we find the total resistance when resistors are connected in series? The total resistance is the sum of the individual resistances. Therefore, the total resistance will be R1 plus R2. For n number of resistors, we add all the individual resistances to give us a total resistance. And this is a typical circuit where components are connected in series. We have the battery, the switch, two bulbs all connected in series, and for a circuit like that, we are going to have same current flow through the entire circuit. Now let's look at parallel connections. For parallel connections, the circuit components are side by side and there are alternate paths for current to flow through. The reason is because the components are arranged in parallel, there will be branches in the circuit, and so current would usually have to split so that we'll have some go through the different branches and pass through each component of the circuit. So first, let's consider cells in parallel. Unlike for cells in series where we have the positive terminal of one cell connected to the negative terminal of the other, for this combination, we say that the positive terminal of one cell is connected to the positive terminal of the other cell, and the negative terminals are joined together. The total voltage for cells in parallel is equal to the voltage of each cell in the circuit. So what it means is that even if you join 10 cells in parallel, the total voltage is going to be equal to just one of the voltages of the cells. And that is why we have the relation Vt is equal to V1 is equal to V2. For resistors in parallel, we see they are joined side by side. The current splits at the junction. We have I1 flowing through R1, I2 through I2. At the other side, these two currents combine to give us I again. I is equal to I1 plus I2. The sum of currents moving away from the junction is equal to the current moving towards the junction. And this is referred to as Kirchhoff's current law. To find the resistance of resistors in parallel, it is equal to the sum of their reciprocals. So we have for n number of resistors, 1 over RT, which is the total resistance, is equal to 1 over R1 plus 1 over R2 plus all the way to 1 over Rn. If you have just two resistors in parallel like we have shown, then you can simply find the total resistance using the relation product of the resistances over the sum of the resistances. So RT is equal to R1 times R2 over R1 plus R2. In this circuit, we have some components in parallel, two resistors in parallel, with a voltmeter across them to measure the voltage. An ammeter is connected in series, as I explained earlier, to measure the current in the circuit. You have a bulb connected in series with the resistors, we have a battery, and we have a switch. The source of current in the circuit can either be DC or AC. DC stands for direct current. And what that means is that current flows in just one direction. So if you have a cell or a battery connected in a circuit, it will move from the positive terminal of the cell to the negative terminal, and that is how it's going to move all the time. AC means alternating current. And what that means is that current changes direction. It doesn't flow in just one direction. For alternating current, the direction of the current reverses regularly. So over here where we have negative polarity, you see current moves in a particular direction. Then when the polarities change, current moves in the opposite direction. The symbol there is the symbol for alternating current. And alternating current can be produced in generators. The normal currents that flows in our homes are alternating currents. So this has been a very good introduction to electricity. We are going to dig deeper when we consider into detail what resistance is, what potential difference EMFs are when we delve into power. So thank you very much for watching this introduction to electricity. Please don't forget to subscribe if you haven't already done so. Like the video, and I'll see you in the next one.